Module 1, Session 4. Learning Outcome 1.1.4. Convert the form of complex numbers. Learning Outcome 1.1.4. Convert the form of complex numbers. Let's have a look at how we convert the form of a complex number. This topic was covered in Level 3, but let's take another look at it. You could ask your class if they can give you the steps to test how much they remember. To convert a number from standard form to polar form, we follow these steps. Step 1. Draw your Argand diagram. Step 2. Calculate the argument theta, where tan theta is equal to b divided by a, therefore theta is equal to the arctan of b divided by a. We get this from our TOA ratio. Remember, for quadrants 2, 3 and 4, use your cast rule and your reference angle. Step 3. Calculate the modulus, where r is equal to the square root of a squared plus b squared. Step 4. Write the complex number in polar form. Z is equal to r cos theta plus I sin theta. Or you could do it in cis form if you prefer. Now let's take a look at the reverse, from polar form to the standard or rectangular form. Can your students remember the steps from Level 3? First, start with the form Z is equal to r cos theta plus I sin theta. Second, remember that r cos theta gives us a. This is the real part. Step 3, r sin theta gives us b. This is the imaginary part. And lastly, we substitute the values of a and b into the standard form equation z is equal to a plus bi to get the answer. Let's take a look at a practical real-life example that requires us to convert from polar to standard form and then from standard form back into polar form.
If two electric potential differences measured in volts are given by 80 volts at 15 degrees and 60 volts at 225 degrees, calculate the resulting potential difference. Now this is adding complex numbers. Therefore, we can express this as Z equals to 80 at 15 degrees plus 60 to 25 degrees. Furthermore, we know that Z is also equals to, in this case it's going to be 80, open bracket, cos 15 degrees plus, actually it's going to first multiply by I because it's imaginary, I sine 15 degrees. The same applies for this second part. Once we have done this, then we have to understand the following concept again. And that is, we must find the value of cos 15 and sin 15. We're going to write it to 3 decimal places. This is this part plus .258 I, because these are your imaginary axes. That is done, then we come to this part. negative 0.707, and then we come to this second part. Again, negative 0.707i, close bracket. Once we've done this part, we're therefore going to have to multiply into the brackets throughout. This becomes 77.28. This becomes 20.64i. This is done. Then you come to this one, doing the same thing. Which becomes negative 42.42. It's exactly going to be the same answer here, except it's going to be including I. Okay, so coming here now, we're going to just collect our like terms. This is that, and then it's going to come and match up with this one. Followed by let's take the differences then. Okay, now we have found the real axis as well as the imaginary axis in terms of Z. Let us just demonstrate with a rough sketch what this means. So these are your real axes, these are your imaginary axes. Let's quickly set this. So which means that for your real axis, you're going to have 34.86. So let's say it's here. For your imaginary axis, you're going to have negative 21. So negatives are here. Which means that these 2 points, actually this point, which is these two values, they form a point here. Now there's a further step we need to take here to expand our understanding, which means that we're going to have to measure the length of this line. This then becomes R. So let's now find R. We know that R is equal to we know that, which therefore makes it straight from our calculator, we can get the solution to that. the value of r then becomes 3 decimal places. So what does it mean? It means that the length of this line is 41.105. Then, which means that we have measured our angle like this. This is what it means. Then we need to find this angle here. We can call that alpha. So let's find the magnitude of alpha. We're going to need to find 10 then. So 10, alpha should be equal to opposite side over the adjacent side, which should be opposite. It's going to be negative. We can just keep it as real number, as positive numbers. So we can just say 21.78 over, so we're going to use absolute values here, over 34.86. That's why I omitted the negative sign here. I'm using absolute values, which therefore makes it so 10 alpha is equal to 0.62478485337. I always encourage students not to round off at this stage, because you're going to need this actual value to find the angle of alpha, making it alpha then would then be equal to of which in your calculator, you're just going to say shift, press 10, go to answer, close your bracket, equal, which makes it equals to 31.997. Can keep it to those decimal places, degrees. Now, we're then going to say the full revolution. We don't know the magnitude of that angle, so we can call that angle theta, by the way. So this whole angle can be theta. So we don't know the magnitude of theta, but we want to know the magnitude of theta. Then we're going to say the full revolution 360 minus alpha should give us theta. So theta is therefore equal to 360, which is our revolution, minus alpha, which is 31.997 degrees, you're going to ignore the negative sign because I just pressed set minus 360. Now that's the magnitude of theta. What does it actually mean now? To interpret this, therefore, you would then say, in polar form, solving this problem, Z is equal to your magnitude of your radius, which was 41.062 at the angle of 328.003 degrees. That is our final answer, and is demonstrated here.
Here are some more teaching tips on de Moivre's theorem.
When we refer to the positive argument, you can only calculate the correct positive argument if you draw the Argand diagram. If you use your calculator, in some instances you might get a negative argument. To counter that two words, to get it positive, in the case of that, you just add 360 to it. But when you construct your Argand diagram with the knowledge of the cast rule, you will get the exact value which is positive of that argument.
Now let's try an example with de Moivre's theorem that requires us to convert the form of complex numbers. Simplify the following by using de Moivre's theorem and give your answer in standard form. 3 minus 4i to the power of 5 times 1 minus I. Give your feedback on any problem areas to the class.
Let's look at the following example. Simplify the following by using de Moivre's theorem and give your answer in standard form. Now, if you don't read this question correctly, you will start multiplying that 3 minus 4i 5 times, and you're going to multiply the whole time. The key word in this question is de Moivre's theorem. Immediately, when you see de Moivre's theorem, it is linked to polar form. Both these expressions here are in rectangular form. So my very first step is I need to convert each one to polar form. When you convert to polar form, the first thing that you must calculate is your modulus. So R mod is equal to the square root of real squared plus imaginary squared, and that is equal to 5. Then you must calculate your argument. But before you can calculate your argument, you need to have some idea of where this angle lies. And that's why you're just going to do a rough argand diagram, because they haven't asked you to sketch the argand diagram, but you want to get an idea. Your real part there is 3. Your imaginary part here is -4. Which means this angle, which is your argument, will fall in quadrant number 4. So you're going to apply the same rules as it was the case for trigonometry. Your argument will therefore be equal to 360 degrees minus arctan. Now please people, very, very important, no negative signs after arctan. Imaginary, which is 4, over real, which is 3, and then your answer there in that instance, if you use your calculator, will be 306.870. And therefore, 3 minus 4i is equal to 5 cos 306.870. Okay, now let's check whether this answer is correctly by using your calculator. It's nice always to check. Right, you switch on your calculator. How will you convert this 3 minus 4i to polar form using your Casio calculator? You want to convert to polar form. That's why you can see that function there. You're going to press shift polar. In other words, I'm going to polar form. Then now you're going to punch in your real part, which is 3. And then you're going to say shift comma. That's how you separate your real from your imaginary part. Very important here. Your imaginary part is -4. It means you take it with a sign. Negative. Oh, let me just go back there. -4. And you close your bracket. Polar form, real 3, -4. and now you're going to press equal. You can see there your modulus is equal to 5, which is correct, but your argument is equal to negative 53.130. And I can explain that quickly. Your Argand diagram, that amount there will give you that 306. In other words, the value that they've given there is this negative 53. So what does that mean? You add 360 to it and you will get exactly the same value. I hope that is clear to both of you. Now let's convert the second one. Convert. One minus 1i to polar form. Once again, the two components, you must first find your modulus, which is equal to the square root of real squared plus imaginary squared. We can leave that in the square root form. Otherwise, you're becoming a mathematical thief because you will round off, and that means you're stealing, because we haven't solved the final problem as yet. Then your argument, you people can see the format of these two complex numbers are the same, so you're also going to use quadrant 4 in order to calculate your argument. So we're going to use exactly the same diagram there because it's going to be positive 1, negative 4, but the quadrant is exactly the same, and that is what we are interested in. 360 degrees minus arc tan of, obviously it's going to be 1 over 1, which will be 1, and you will get a nice answer there of 315 degrees. Right, let's test this one. Let's go to your calculator. Shift polar, the polar form of, and then it is 1, shift, and then negative 1, close, let's check. Real part 1, imaginary part negative 1 equals 1.414, that's the equivalent of the square root of 2. And then let's just see, negative 45, obviously negative 45 plus 360 degrees will give me 315 degrees. It's advisable always to use the positive values. Now we can move to our, both these are in polar form, so now only we can apply the Moivre's theorem. Therefore, okay, 3 minus 4i to the power 5 multiplied with 1 minus I is equal to bracket 3 minus 4i, that's 5 cos 306.87 degrees. That is to the power 5. Then polar form here, the square root of 2 cos 350. I think you've seen there I've left out a step, but it's modulus cos argument, which will give you, now this is the power rule of the Moivre's. I first need to simplify this. What's going to happen here? When you raise to the power, it means that your modulus will raise to that power, but your argument will be multiplied with that power. and then times that square root 2 cos 315. Close bracket. And you use your calculator for 5 to the power 5 and you get 3125 cos, and you use your calculator 5 times 306.870 and you will get 1534,350. And you will multiply it with the square root of 2. Okay, cos 315. So we have simplified. In fact, we have already applied the Moivre's theorem. Now we continue. Can I continue on the other side by writing equal, because we need space? We have now the product of two complex numbers. How do you do that? You multiply the two moduluses, 3125 times the square root of 2, and cos, you're going to add now the two arguments, 1, 5, 3, 4, 3, 2, 5, plus the 315, plus 315 degrees. If you use your calculator, you will get 4419,417 cos. If you add those two, you will get 1849,350. Hey! Hey! Now you will see that 18349.350 degrees is completely out of range. In other words, we need values between 0 and 360. This is, what do you do now? You're going to subtract by 360. In fact, seeing that the calculator is here, I will do an illustration how I will get to my angle value. Let's go to the calculator. Let's take that value, 1849,350 minus one cycle, which is 360, equals, right? Minus another cycle, which is 360, equals, right? See, still outside. Minus another cycle, which is 360, equals. Still outside. Minus another cycle, equals. Still outside. Minus another cycle. You can see there, it gives me 49.35 degrees. But did we answer the question? Yes, but your answer should be in standard form. Now we're going to look at the meaning of cos. What is that? 4419.417. The C means cos of that 49.35 degrees. Plus, can I just write at the bottom here? Again, 4419.417. Obviously, I sine of 49.35 degrees. And if you use your calculator, then you will get 2878 3.970 plus 3353.025i. Now let's check whether we have convert correctly from polar form to rectangular form by using the calculator. So we want to convert now to rectangular form, so you're going to have shift rectangular, and then you put in your modulus first, 4419, 417. Then shift, then you put in your angle, 49.35. You close, you first double check, and then you say equal. You can see there your x value, which represents your real part, is 28.78,9. You can see that there's an 8, that's why it becomes 970. And then you move to your y value. You can see there 3353.025i. So that is correct.
Teaching tip on calculators. Remember that students always need to show all the steps in arriving at the solution. The calculator is only used here to check the answer for the conversion from one form of complex numbers to another. In the previous example, the lecturer checked his workings using a calculator. We have used a Casio FX82ZA Plus. If your students are using another kind of calculator, they should look inside the calculator manual to find out how to do these conversions to check their answers. Close of Topic 1, Module 1.